So then, what kind of things do we have in Kotlin that are really different from Java? Some language constructs that can be quite interesting. The first one I'd like to talk about is these companion objects. I mentioned it before. And in Java we have static members and static fields, and one thing I know about static is that it's very confusing for students. Hard to see what we're talking about. So companion objects basically are Kotlin's approach to this. So they are less confusing because we don't have to sprinkle static everywhere. There are some disadvantages in some cases, but in general it's less confusing. So in general we have these objects. So hopefully you remember I did talk about it before. So an object is just Kotlin's implementation of the singleton. So there will only be ever one instance of an object, and it's created automatically. The first time you use it, the JVM will load it and then initialize it. So you can treat it as if it was created at the start of the program, even though that's not technically how it works, because the JVM loads your code on demand always. But what does this companion object do? So a companion object is an object that is linked to a class. That's why it's a companion. And you can actually have named companion objects. You saw that with parcelable. So if we have parcelable, we can give it a name. So we link this object to this class. So we make this object available through the companion. So if you create a companion object, it also creates a companion field on your class. Or if you do type.companion, you get the object. From Java you get the field. The interesting thing that distinguishes a regular object from a companion object is the companion object actually has access to the private members of a class, and you can access the members, the elements inside the companion object as if they were on the object itself, like you would do static methods in Java. You can do type dot thing. You can do type dot companion dot method or type dot method. It's exactly the same. So it replaces these static fields and methods in Java, but a companion object is actually an instance of a class. It just happens to have only one instance. And because it is an object that implements a class, you can use inheritance with it. It can implement an interface, like for parseable, the creation interface, so the creator interface. And you can inherit classes as well. So there's some really interesting things you can do with these companion objects. And of course, inheriting code is always helpful for that. Then we have operator overloading. So what we'd want to do is so basically, what is operating overloading about? Operator overloading is basically the idea that we want to define our own operators in some cases. So we have all these plus, minus, times, divide for integers and other primitives, but sometimes we want to define our own ones. And that is what operator overloading can do. So sometimes we also so why do we want that? So sometimes we have our own number types, or Java has those already. There's something like big decimal, or big number, so a big integer. Those are numbers that are bigger than a long can contain or a double can contain. Arbitrary precision numbers. They are still numbers, but we want to be able to handle. There's complex numbers as well. So in Java we have this really clunky business with when you use big decimals or big integers, where you actually have named functions rather than the operators, and it just makes things look very messy, very clunky. So we want to have our own operators to kind of make this much clearer. Kotlin does not give you the freedom to define any operator you want. There's other languages that do allow that. An example for the JVM is the language called Scala. That also means that you can go completely overboard and make things become a big mess. Don't do that. So Kotlin only has a fixed set of operators. What you can do, by the way, is have infix functions. So you can have a function that actually allows you to basically have a receiver and a parameter and then not have the dot and parentheses needed. You just type the name. It's quite helpful. There's a function, default language function that does that is, for example, to. So A to B. That actually creates you a mapping entry that with an infix function, so a pair. So there are many ways, by the way, if you use operator overloading, and then one of the reasons that Java doesn't do it, you can shoot yourself in the foot very well with operator overloading. So try to stay sensible with this. What does this look like? For example, you have the operator function plus, that's addition, function minus for subtraction, times for multiplication, div for division, and dot dot for the is the range to function. So if you have a range, that's how you create that. So if you want to make your own custom range, you implement that, and then can use the dot dot. You have plus assign, etc. And there's many more available. There's logical operators, etc. So have a look at the documentation for that. But there's also a few that are special, and I would put your attention to this. So one of them is the operator invoke. So invoke basically means that you can have an object and you can just use you can treat it like it's a function name and call it. So in Kotlin you could have a way, because these operators, they can also be defined as extension functions. So if you have a SAM interface, in Kotlin you can write the extension function that has the operator fun invoke that then calls this, so that in Kotlin you could actually, using this extension function, make calling the name of that particular interface's method completely disappear from your code. It makes it much clearer what happens, because it effectively is a functional thing, so we should just be able to call it. And if you make it an inline operator fun, then that code entirely disappears from the runtime. Then we have the operator fun get. You have seen this in Matrix, for example, where you basically use this to get array indices. So you can have multiple indices, and that will translate into multiple parts between the square brackets. So in this case, the operator fun get index gets our value. Operator fun set sets a value. And yes, you can have multiple implementations of these that take different parameters, either different value types or different index types or multiple indices. And I think Matrix does this, for example. It has one get that takes a coordinate and one get that takes an x and a y value as separate integers. So those are these special operators. So with this you can basically make your types a lot easier and to read from a user's perspective. That's what we want. We want making use of a class become really clear and easy. Then, transparent factories. So what are factories and why do we want to make them transparent? So factories, I'll come back to that a little bit because that's our code pattern of the week. So a factory is basically a thing that creates an instance of a class. And there are some cases in Kotlin, I don't know if you've noticed, but if you have a constructor that basically the first thing you have to do is call the parent constructor. Sometimes what you want to do is do some calculations before you do that so that your parameters can be translated properly into the parameters for that parent constructor. Sometimes it's possible to actually use use secondary constructors to do that transformation for you in some forwarding way. Make them private, obviously, or make some of them private if they're only for internal use. But in some cases that's just not really easy to do. So if you want to get these field values, you might want to basically have a way of creating an instance of that thing that does a calculation and then actually creates the thing, but does so transparently so that your users don't need to care. And that is what these transparent factories do. And what we can use there is so in another case is what we call reified types. I'll come back to that again later. What are reified types? But basically sometimes you want to be able to do that. I will show you some examples later. And in general, the third reason why you might want to do this is sometimes you can actually reuse instances. Either because you have a cache of the last values, and if it's an immutable object, there's no reason to create yet another one of the same immutable object. Sometimes we have a constructor that takes an interface, but the object itself implements that interface and can be a wrapper for those things. So like we have an object that has a handle, and the object itself is a handle to itself, but you can also have a handle that doesn't point to it. So what you can do in such a factory would be able to say, okay, is this handle actually already an instance of this class? Then return myself. Otherwise, I'll create an object that looks up the thing, etc. So that is, or creates a new handle, whatever needs to happen. So basically you can have more flexibility. Or in Kotlin example, we have the list of factory. That's not a transparent factory, but it is a factory that creates as a list of elements. But if we give it 0 elements, it creates a special type that's only for empty lists. If we give it 1 element, it creates what we call a singleton list. Again, a list that only has 1 element. It doesn't store things in an array, it just stores 1 element. Only if you have 2 or more elements, it will use a different type. And it could choose based upon whatever it wants, what instance it's going to use. But that's not a transparent factory. So yes, by the way, if you have questions, please put it in the chat. I can read the chat. So you can even answer it from each other. Anyway, so how can you do this? So there's kind of 2 ways that you can do this. The first way is to actually have a function that's just a free function that makes this work. So we have our class that we give an internal constructor because we don't want this to be our public interface. In a way, we would want to have a file visibility, but so where we can have a private class, and then the function A would be able to see the private class because that's private to the file. If we make it it's a private constructor, that private would be private to the class rather than to the file. So we need it to be internal in this case. Yes, some more visibilities would be nice. Then we have this function A that functions as a constructor. So we give it a capital A name. We give it the same name. That's valid in Kotlin. But we cannot really do this in Java in a way, but we can do this in Kotlin. And it looks exactly the same. So make sure it behaves as if it should here. So why we would want to use a private constructor? Basically, you use a private constructor in a class when you have another constructor that's not private, and you might want to do some checking before you use the private constructor, or you have a factory function that is inside a companion, and then it can access the private constructor. If you want to police how your objects are created, you make it private. Obviously, you need to then provide a way for those objects to still be constructed. Normally that involves either secondary constructors that are not private or primary, or the companion object. So in this case, what we do is we have a number as a string, and then we check, is this start with 0x, then we make an integer as if it is a hexadecimal. Otherwise, we give it if it starts with a 0 only, then it must be an octal number. These are Unix conventions, doesn't really matter. And otherwise, we just say it's a decimal number, and then we create an object with that number. And it takes a null value. And here is also where you can see we have the constructor parameter x and we have the property x. The parameter takes a nullable int. The property is actually a non-nullable int. And this is one of the cases where you say I actually want to declare the property and the constructor parameter. And constructor parameters are only visible inside the main line of the code where you have this initialization of your object. So don't do really surprising things and it works well. So you don't need to give it a different name. It knows that this x that you assign to x is the constructor argument rather than the property. If you look in IntelliJ or Android Studio, you will see that they will actually get a different color there. So you can visually distinguish that this is a parameter and the other one is an attribute. So the formatter I use for these slides doesn't distinguish that. It doesn't look at the code that carefully. So, and yes, you could also instead use an extension function upon a companion object. Because in Kotlin all objects have a companion. So, or kind of sort of have a companion. But it's kind of pointless to do that because you can define it on the companion itself, or you can have a free function. From Java, an extension upon a companion is not really useful at all because you don't want it to actually need companion state. So how you use a companion, basically the same. So in this case, the constructor could have been private. So there's an advantage of doing this. And here we see also that we use the JVM static and the JVM name parameters. So JVM static makes this available as a method on the A class from Java. And then we have the JVM name where we call it, we call this a function not invoke in Java, but we call it off. So in Kotlin it thinks that this function is called invoke and it's an operator. And we want it to be an operator invoke because then we can just create it as if it is just a constructor. It looks like it's a constructor from the using code. Not in the compiled code, but in our source code. But in JVM, one of the ways that you can create an object or convention is to call it off. So we get a.off 8. So we get whatever object belongs with that. And that's one of the ways you can have a factory. I mean, there's different conventions for factory naming. This is one of them. And so it can make natural Java access. It's slightly less straightforward, but it does allow you also to have private constructors to kind of close it off really except for inside the class. So it might be better to do this rather than having the free function. Although free functions are also quite popular and work well as well. Then generics. So what are generics about? So generics are about the ability to kind of create a family of types. So we call it, officially it's called a dependent type. So you have a type that's dependent on parameters. So basically you want to give parameters to a type. So this is not a type that is single but has parameters. So a common use case for this is like containers and lists, but there are many other cases. If you have arrays with a particular length, you might want to have the length part of the type. You cannot do that in Java or in Kotlin, but there are languages where you can do that. What we can do is types as parameters, and what that does, it is creates a family of types that are mostly the same, but they are not the same. So we have a list of integers and a list of strings. They are different things. Integers are not strings and strings are not integers. So you can't assign a list of strings to a field or a variable that expects a list of integers or the other way around. And when we look at the setting values, it becomes even more challenging. So basically that's what generics are about. So a very basic example of kind of how this works is this example of code where I actually use it with parent-based child classes. So how you could do this instead. And you see the clunkiness that we get. So we have this base class that has basically an array of elements, has elements. So this is a very, very, very basic implementation of lists. You don't really want to use this, but it's slideware. Code that fits on your slide. It has to have some restrictions because of that. So we have this storage, that's an array of 20 elements. And then we can get elements out of that using the get operator with a single index. And then we read the element out of that, and we have a doSet function. This one is protected. This function is only valid to be called by child implementations. So base list could have been abstract even. Maybe it should have been abstract. Not because it has no implementation for anything, but because it is not valid in and of itself. It's not usable because you can't change values. So maybe I should have made the example to be abstract. Then we have the string list that actually implements this by saying, okay, when we get the thing, I am going to guarantee it's a string. So I do the casting. If you use generics, even in Java, the caller will do the casting effectively. If the caller says, okay, this is a variable that needs to contain a string, and this is a list that I know is strings, but it's actually the raw type is object, it will do the casting. So in this case, the casting happens in this type rather than in the user, but the end effect is obviously the same. So we have, in this case, we need to do the cast to the type because we have an array of nulls. We know it's not a null or an object. We know that it's a string or a nullable string because the only way to set values is through the set operator. The set operator takes strings, in this case not nullable ones, so Okay, yeah, maybe it should have taken a nullable string. And then that set operator calls the doSet. And this class should be final. Should not be inheritable. So this is the way it works. But it always becomes a little bit clunky. And if you have a chain of derived types, it also doesn't really work that way, and compatibilities start to become really tricky, and you need to have extra interfaces for only reading rather than for reading and writing, etc. So, and it is a lot of writing work, and generics basically takes this all away, and it removes a lot of needs for casting, because before we had generics, when you use the list, you actually had to cast the value you get out to the right type that you knew it was, but the language couldn't tell you. So our generics, when you have these generics, when you have these type parameters, so you put them between the angular brackets, there's two ways of implementing that. There's one way of calling it reified. Basically, that means that you actually somehow push this type parameter into the code. That you actually say, okay, I'm not creating a list of any and then doing casting. I'm creating an array of that particular type. I am using this type as a base point for my code. So we record basically what the type is, and we actually implement variants. And obviously those implementations have all the things to make it work correctly. Because one of the things you can do with these families is that say, okay, there's a lot of code that is really the same, or I know I'm getting something that at least if I use a getter, I will get an object. It can be a string, an integer, I don't care. I can work with that. Or whatever is the type, that's also what I'm going to return. So there's a lot of things you can do with generics and generic functions that can kind of keep track of, I know what the type actually is, and I'm going to use that later on. And for that you do not need reification. Reification really means that you can, in the implementation, know what the type is. You can inspect what the type is, that is the type, that's the parameter. The other option is erasing that information. That's what Java does. So when we look at the JVM level, for most intents and purposes, the generic parameters are gone. You can actually do it if you create an object that has no generic or class that has no generic parameter, but implements an interface that has a generic parameter, or a parent class that has a generic parameter. You can then figure out what the value of that parameter was, because this particular class has no variance, and it can then look up through reflection what the type was. And so you can kind of do it in a manual way. Not ideal, because you have to have a class for every version, whereas reified generics like C# does this all automatically for you. And it doesn't even happen by the compiler, it happens by the runtime, because the runtime can do this. And one of the big advantages, it can work properly for primitives as well as for objects. In Kotlin it kind of works also for primitives, but not as efficiently as if you use the primitives variants of this. So sometimes you want to know the type, so one of the ways that you can do that, or a poor man's version of this if you don't want classes, is to just in your type record the type parameter with a class field. So you record the type that you want to use, and then you have your reified type. So how does that work? Because it's something you surprisingly often want to do. So for example, we can do that in a function, in particular this filter is instance function. So this is a built-in function into Kotlin, and I have just copy pasted the implementation. I've removed all the documentation to fit it on the slides. So we can get all strings out of this list. So this will print string only. And all the integers, that will print 2 and 5. It won't print 5.0, it won't print 3L, it won't print string. So this filter as instance is implemented as 2 parts, just because they find this is an easier way basically to share the implementation. So filter as instance is implemented as a filter as instance 2 with an array list parameter. The array list is just where is this going to be stored, and that is returned as a return value. So the filter is instance 2, because normally you don't care about passing a list where you want to add the elements to. Sometimes you do, because as you can see, that list doesn't have to be empty initially. You can add it to things. So if you have multiple sources where you want to get your stuff from, this is a way in which you can make that work correctly. So what this does, it will create as a list of the elements of that particular type. And filter as instance 2 basically checks for every element in the receiver, that's a collection, that is the iterable that it takes. It checks if it is an instance of R, and in that case adds it to the resulting list, and then returns the destination. So that's a type safe way of getting all the elements in that list that have that particular type. But the way it works is that it's done all through reification. That type is basically passed along. In this case it's fully inline, but you can also use the, in this case, C::: class thing to get the class object, and then you can use a class.cast or class.isInstance methods. So how does this work, for example, for a class? So in this case, for a class, we want to store the type. We have this type, and we would use so we have this type, and then we want to hide the use inline factories to make this hidden. In this case, we don't care about making this constructor private, because maybe sometime someone wants to explicitly pass a class rather than using the reification. Sometimes you do only have a class object, and that's valid as well. So this particular is just a collection that checks the types of an element before you add it. So because generics are erased at runtime, there's no actual checking when you add stuff. It only checks when the values that are received from the element are used or stored. So the user may check the type, but it's normally much better to check the type when you add elements rather than when you get them out. Just the cause where you put the wrong element in is much closer to adding than you do a lot of code, and then at some point you're going to read something out of the collection. So in this particular case, what we do is we check, is this type, so is this element an instance of the type, and if that's not the case, we throw the illegal argument exception, and normally we just add the element and we just from the data, so it's just a delegate pattern. So that is how we do that, and this is then how you would actually hide it away with an inline factory. So we just have a checking collection T that takes a reified generic parameter. It has to be inheriting any, because the type of class T does not allow you to have nullable types. It also does not allow you to have primitive types. So it has to be any. That can be a little bit annoying sometimes, but that's the way it is. So we have a checking collection that checks those types. So here you see how that works. And then of course that collection is the same as on the previous slide. So we just have this very quickly. We have a reified factory.checking collection, and with the parameter. Okay, so, or it should not be, it should not have reified factory dot, actually. I think this is a, just, when I wrote this, it was a completion thing. So it just be checking collection. I will fix this in the slides later on. Then a very cool feature that we have is delegate properties. So what are delegate properties about? Delegate properties are about when you have properties that you want to have getter-setter behaviors that are actually always the same. So you want to be able to reuse code. But obviously there are separate properties and there are some bits that are not the same, obviously. And what you can do is basically use delegate properties. So delegate properties, what they do is they allow you to have a, rather than having to write the getter setters yourself, what you do is you have an object that has a getter and a setter inside it, or only a getter obviously, that then gets called when you get or set that property. And those implementations can then reuse that code in whatever way is appropriate. So we want to be able to basically reuse property getter and setter implementations. So by using classes for that. So what is required to make this work? So you need to have basically the delegate needs to have an operator get value with this particular signature. It needs the parameter this ref. So look also at the documentation of course, that passes it the implementation of that operator will get the reference to the object on which the property is declared, as well as a property object. The property object allows you to look at what is the name of the property, what's the return type. So that's basically introspection you can do there. And it needs to return whatever is the type of the thing that's returned. So yes, that could be a concrete value rather than a generic parameter. So maybe that T actually normally belongs to the class rather than the thing. So, and if you want to set values, that kind of works basically the same with set value. And that's all you need to get a delegate property. You need to have these operators defined. They can be either members of the class or they can be extension methods. So if you have a type that you want to use as a delegate, you can actually write an extension method that allows you to use it as a delegate. And there's some really interesting example with maps. Because there's some standard delegates. So there is, for example, the lazy delegate. I showed you this one before for the lazy pattern. So the lazy delegate implements the lazy pattern for you. So you have a property that's lazy. You just create lazy. It takes a lambda as a parameter. How do I initialize this value? It takes a function with the initialization, but that will only be called once on initialization. And the interesting thing with this implementation of lazy, it actually has a number of options, and you can basically, it is by default, it is thread safe. You can ask it to create a version that's not thread safe, and it won't do any checking when initializing it. There's different ways of making this work correctly with lazy that you would really not want to implement yourself time and time and time again. It's kind of tricky to get that right, and it's always the same. So lazy is a very, very useful delegate to use if you want a variable that is expensive to calculate, and you maybe not even know that you need it. Or sometimes there is the case that when you initialize your class, you cannot validly create it yet because some other properties need to be created first, or there's a circular dependency of some sort. So lazy can often help with that. Then there's observable. So observable allows you to basically have a property where anytime it's changed, this will trigger a function to be called. So observable takes some parameters that basically say, okay, this is what gets invoked or informed when there's a change. Very useful if you have objects that basically inform views that their content has changed. So you make the attribute observable, you make that the implementation of the observer, then send a message to the to your registered observers, and then from a property change we can observe changes of the entire class. And one thing that Kotlin implements is the ability of using instances of the map interface as a delegate. This is implemented as extension methods on map. So how does this work? So it only maps with a string key. What it does, it basically, when it needs to get the value, it looks at what is the name of this property. It uses the name of the property as a key into the map, and then it gets the value or sets the value for setting. So that's how you can use a map as a way of representing your data. It's not the most efficient way of working, but sometimes if you have a map and you might want to expose those as properties, it is a good way of dealing with that in that particular case. And this is built in. You can also very, very easily write your own ones. There's a very, very interesting element as well, that is delegate providers. So sometimes you want to be able to actually, so a delegate gets to inspect when you get or set a value. But sometimes, and the function that creates the delegate creates a delegate, but that function cannot inspect the property it is created on. So what you can do instead is this auto operator that is provide delegate. So when you create this delegate, so by the way, a delegate you do is like property X by this particular function that creates me a delegate, or a constructor that creates me a delegate. So what provide delegate does, it basically allows you to create a delegate. In this case it's a member delegate, so a resource loader might in this case actually say, okay, if you want a delegate, I need to check that this property actually exists, and then it creates a resource delegate that actually gets that property. That's the actual delegates that is used. So you basically, in provide delegate, you get to kind of provide a map between an object that is used to create a delegate. So when you create an object with provide delegate, you have an object that then somehow has this provide delegate method that then will create as our actual delegate. And this allows us to kind of be there in the construction phase. And this can be very powerful. One of the things is that in the construction we now know the property. So if we look at the class myUI, what we can see here is that we actually have the bind resource id.imageID, but we actually now already know the name. So the check property can check that the image name exists at that particular point in time. So so the alternative would be that we would actually have to pass the name as part of this. So check property can here check this. Or sometimes if you want to have a class that can know about its members, then it's important that these names are registered. or you want to have a property, a delegate that knows its name, that is introspectable rather than, okay, on getting and setting, I get this property, I want to always have this name, then you need to use provide delegate. And so this case, so bind resource knows the name of the property it is being used on. That's what provide delegate gives us. It's a quite advanced technique, not something I would expect you to use for your assignment at all, but it's quite interesting and useful.